Bismillahirrahmanirrahim. Electrical network analysis, and today our topic is high pass and low pass filters. Okay, so what are the filters? Any combination of passive R, L, and C elements, or the active elements, that is the transistor and operational amplifiers, etc., are combined to design to select or reject a band of frequencies, so called as the filters. As the name reveals, it filters out some of the frequencies, and some have been rejected. That's why it is called as the filter. So it filter out the frequencies only. Okay, it filter out the frequencies only. Okay, it is specially used in communication system. In communication system, the desired information frequencies are accepted, are allowed, and the higher frequencies of that is used for modulation purpose have been rejected. So, similarly, in a stereo system, the filters can isolate particular bands of frequencies for increase or decrease the emphasis by the output acoustical system. And the filters are used to filter out any unwanted frequencies, commonly known as noise. This is the undesired frequencies, which is termed as noise in the communication system. Due to the non-linear characteristics of some electronic devices or signal picked up from the surrounding medium. In general, there are two classic classification of filters: the passive filters and the active filters. So, in our course, we will study the active filters only. Okay, move to the next slide. Uh, there are four types of basic types of the active filters. Sorry, the passive filters. So the one is a low pass filter, and the other is high pass filter, the pass band filter, and the stop band filter. Uh, their name reveals their functions and their curve. So it is a good point for the name, that their names, there is a hidden knowledge in the name, and for its function and the curve. So low pass filter, it means it will pass the low frequencies, and definitely it will block the higher frequencies. Uh, Here is a graph for the low pass filter, voltage against the frequencies. These are the low frequencies, mean low values of the frequencies, and as soon as we are moving here, the frequencies are going to increase. So, uh, uh, for example, this is the low frequencies, so it means it gives us the output for this frequency range, and for this frequency range it it stop this band, it doesn't allow this band. So this is called as the low pass filter. We will study it in detail, the circuit diagram, some other equations and the numericals for the low pass filter in the upcoming slides. Similar is the case with the high pass. The name revealed that it will pass the high frequency and block the low frequencies. So these are the low frequencies, and it has been blocked. And this blue shaded region means it has been allowed by the filter. So these are the high frequency range. So it has been allowed by the filter, and this portion has been blocked. Okay, this is also the V output or frequency graph. Pass band filter. It means it passes a band. Band means a range of specific range of frequencies, and block the rest of the portion. For example, if you want to allow the frequency from f1 to f2, so this region has been passed out, while the rest of the region below f1 and above f2 has been blocked by this filter. So this is the quality of pass band filter. And the stop band filter, as these two are the reciprocal of each other, similarly these two are also the reciprocal of each other. The stop band filter mean it stop a specific range or specific band of frequencies and allow the rest of the band. So uh, the portion that has been blocked by passed by the pass band filter has now been stopped or blocked by the stop band filter and allow the rest of the portions. For example, if you want to stop a range from f1 to f2, so it will stop this range and allow higher than f2 and below f1. So this is the whole story of the filters. Okay, now in detail we will study one by one in detail. The first one is the low pass filter. So now this is the RC circuit, but we will get the output from the capacitor. If you get the output from the resistor, so it won't work for you as a low pass filter. Now, so it is mandatory. Why it is mandatory that we should get the output from the capacitor? Because look at here, at low frequencies, for example at zero frequency, as we already know that X is inversely proportional to the frequency. So for the low frequencies f is equal to 0, the Xc will be infinity. So infinity means a huge amount of capacitive reactance. So it means the circuit will act as open circuit, because a huge means the air has infinity impedance. So it will act as an open circuit. So no current will flow. I will be equal to 0. When I equal to 0, it means there will be no drop in the resistor as well. No drop, because the drop in any of the element will occur only and if only if the current is passing through that element. As there is no current is flowing through the resistor, because it acts as an open circuit. So the output voltage will be equal to the input voltage, means V out is equal to V in. That is the case for low frequencies. So uh, look at here, low frequencies means the output will be equal to the input. Okay, this is the input voltage. As soon as the frequency is increasing, the sum of the drop will appear here. So it will no longer will be an open circuit. So some drop will appear, the current will start to flow. So the Vi will then be less than, because some of the drop will appear over here, Vr, as Vr. So then the V not over here will be less than Vi, because some of the drop will appear uh, over here. Okay. uh, okay, now consider the higher frequency. At higher frequencies, the f, for example f is infinity. So for f in infinity, X will be equal to 0. Anything divided by infinity is equal to 0. Okay, so uh, this means at higher frequencies there is no drop. X is equal to means there is no drop, so that circuit will act as the short circuit. The short circuit. So all of the drop will appear over here. Vi will totally drop in Vr, and there will be no drop in across the capacitor, so V naught will be equal to 0. So for higher frequencies, for example, this is the infinity. So for f is equal to infinity, the V out graph is equal to 0. So this is the graph for the low pass filter. Means for low frequencies it will act like this. The output will be equal to Vi, and with the increasing of frequency, the Vi is going to reduce, and for very high frequencies, means the high frequencies, the V naught will reduce to 0. Okay. This is the gain. What does the gain means? Gain is the normalized gain. Means the output divided by the input. We output divided by the V input. So we call it as normalized gain for the voltage AV. Okay. Now in this case, we have to divide V naught by Vi. As we know that for f is equal to 0, V naught is equal to Vi, as we have discussed in the previous slide. So V naught is equal to Vi means, if let's suppose V naught is equal to 10, so Vi is 10, then V naught will also be equal to 10. So 10 divided by 10 is equal to 1. So always at f is equal to 0, the AV, the normalized gain, will be equal to 1. Okay, now FC. What is FC? We have to go to the previous slide. F FC. This is the critical frequency, or we can say a cutoff frequency. So at cutoff frequency, this is the case when x xc is equal to r. This is the case when xc is equal to r. This case x is equal to r. So at this frequency xc is equal to r. Okay. At any intermediate frequency, for example, at any frequency, V naught is equal to, by voltage divider rule. Let me type it first. For the simple series circuit, we are getting the voltage across the capacitor. So according to the voltage divider rule, according to the voltage divider rule, we are taking voltage across this. So V out will be equal to xc, voltage, so impedance of the output, divided by the series, these two, r minus jxc. So xc divided by r minus jxc. For in polar format, xc minus jxc means xc at an angle of minus 90 degree times Vi. Okay. This is the voltage divider rule, divided by r minus jxc. So for in the polar format, r minus jxc means r square plus in polar format, r square plus xc square whole square root, and at an angle of minus tangent inverse xc divided by imaginary divided by the real. So by dividing this by this, okay, now we are actually finding the AV. So dividing Vi on both side, so it will be AV, and it will be cancelled out. So by dividing these two. So this will be the r, and minus tan inverse on on the numerator side will be plus tangent inverse xc over r. This is minus 90 degree as it. So uh, this is the actual AB. Okay, now uh, taking xc common from the numerator, so xc over xc, and this will be also divided by xc. Okay, so this xc will be cancelled out with this will be with this, so 1 over r, and this will remain as it is, r over xc whole square plus 1. Okay, and the phase angle theta will be equal to minus 90 degree plus tangent inverse xc over r. Okay, so by trigonometric rule, minus tangent plus minus 90 degree plus tangent inverse means minus tangent inverse r over c. If you do, you can try it by calculator. Put any value for r and xc. So apply this r and xc over here, and r xc over r over here. So you will find same answer by this and this. Okay, move to the next slide. Let's suppose for the critical frequency means xc is equal to r. So okay, for the case of xc is equal to r, putting x is equal to r, xc and r as same value, so it will cancel out and we will get 1. So 1 plus 1 whole square root means 1 over root square 2 is equal to 0.707. This is the case for the fc. Fc means xc is equal to r. We call it as the critical frequency or the cutoff frequency. Critical frequency or the cutoff frequency. Okay, so xc is equal to 1 over 2 pi fc. So xc is equal to r. So r is equal to 1 over 2 pi fc means fc is equal to by cross multiplication, fc is equal to 1 over 2 pi rc. This is the formula uh, of fc in term of r and c. Okay. Going to the previous, and v naught is equal to x divided by r square plus xc square whole square root at an angle of theta. There is some angle theta, and we are assuming a 0 degree for the vi input voltage. So this is the vi input voltage. So vi and theta will be multiplying, so we will get theta. Sorry, add theta, the angles are added, so theta plus 0 is equal to theta. Okay, so what about the angle at higher frequencies? At higher frequencies, xc is very small, so because inversely proportional, so r by c will be quite large, as at high frequency xc is small, so small means r by xc will be large. So uh, if it is, if you consider a very large value, for example large as much as infinity, so minus tan inverse of infinity will be equal to of infinity will be equal to minus 90 degree, of minus infinity of infinity is equal to minus 90 degree. And now consider the case for the low frequencies. This was the case for the higher frequencies, and now the case for the low frequencies. Okay, so r by xc will be small, R by Xc will be small. So if we consider small as 0, so tangent inverse 0 will be equal to 0. So means for the low frequencies, the angle will be equal to of 0 is equal to 0. For low frequencies, and the angle theta starts from 0, and for higher frequencies it will lead to minus 90 degree. Now considering the case of f is equal to fc, means uh, x is equal to r. So what will happen if these two are equal? So means the value will be 1 minus tan inverse 1 is equal to minus 45 degree. So how the phase angle graph will look like? It will look like as this. For fc is equal to 0 means sorry, for f is equal to 0 means low frequencies, the theta is equal to 0. And for higher frequencies, the theta leads to the minus 90, sorry, 90 degree. Okay, these two are similar, but the difference is only the reference. In this case, v naught lags vi, and in this case the v naught leads the vi. Okay, so the only difference is the reference. So if we consider v naught lags vi, so the graph will look like as this. And if v naught leads to, it depend upon the given value of the theta of vi. Actually we have considered vi as 0 in previous slide, but it is not the case every time. So it may change. So the theta for the vi is not always equal to 0 degree. It may change. So the graph will then be changed accordingly. Okay, so for fc, the theta is equal to 45 degree. fc, the theta is equal to 45, and for the 0, the angle for lower frequencies means f is equal to 0, the theta is equal to 0. So this is the graph for the theta versus the frequency. This is the summary of the low pass filter. fc critical frequency 1 over 2 pi rc. F is less than fc for voltage v naught greater than 0.707. For fc less for f less than fc, the v naught is less is greater than 0.707, and for f is greater than fc in this area, the v naught is less than 0.707. Okay, okay, and at fc v naught lags vi by 45 degree, and fc is equal to r over 2 pi l. This was the whole summary. Okay, now the lr circuit, by getting output from the r, can also act as low pass filter. So you have to done the calculation for this lr circuit, and this is your homework. Okay, okay, now the high pass filter. So in this case, as I have already told you that low pass filter is the reciprocal of high pass filter. So in previous case we were getting the output from the capacitor, but now in this case we are getting the output from the resistor. So considering the case of high frequencies, for example, f is equal to infinity. Yeah. So okay, so what will happen? F is equal to infinity means xc will be equal to 0. Xc will be equal to 0. So xc is equal to 0 means drop. No drop means short circuit. So xc will act as short circuit. So all of the drop of Vi will appear across the R. So V naught will be equal to Vi for F is equal to infinity, means high frequencies. So for the low frequencies, F is equal to 0. What will happen? X xc xc will be equal to infinite, because inversely related. So xc infinite means a voltage drop huge amount of voltage drop can be represented by the open circuit. So no drop will appear across this, because all I is equal to 0. No current is flowing in the open circuit. So let's have a look on the graph of V voltage versus frequency. For high frequencies, the V naught is equal to Vi, as we have discussed in the previous slide, and for low frequencies, F is equal to 0. The V naught is equal to 0. V naught is equal to 0. So that will be the curve for the high pass filter. Now the normalized um, gain a naught av is equal to V naught divided by Vi. So we have to V naught divided by Vi, as for the low frequencies V naught and Vi are same. So sorry, V naught is equal to Vi for the low frequencies. For the low frequencies, what is the case? V naught is equal to 0. So V naught is equal to 0 means 0 divided by Vi is equal to 0. So AB is equal to 0 for the low frequencies. And now for the high frequencies, A naught is equal to V naught is equal to Vi. So V naught Vi will be cancelled. We will get 1. So AB is equal to 1 for the high frequencies. Okay. So by the voltage divider rule, V naught is equal to R divided by R minus JXC, and this is the similar case in the polar format R at an angle of 0, and R square plus XC whole square root angle minus in the polar format minus tangent inverse XC over R. So we will shift this angle to the numerator. So we will get plus tangent inverse XC over R. So now we will take the R common from this. So R will be cancelled out with this R. So we will get 1 over 1 plus XC over R whole square root. Same as we were taking common the XC in the low pass filter. Okay. Now considering the case of X is equal to R, the cutoff frequency. So one, so we will get one from this ratio. So 1 plus 1. Okay. So 1 over square root 2 is equal to 0.707. So FC, this is the case where the XC is equal to R. So now X is equal to R, so R is equal to 1 over 2 pi FC, means FC is equal to same value 1 over 2 pi RC. So this FC is the same as the FC of the low pass filter. Okay. So now taking considering the theta values. So similarly, for high frequencies, XC is equal to uh, for high frequency X is equal to 0, and 0 means tangent inverse. So this value will be tangent inverse 0 is equal to 0. Okay, for higher frequencies this will be equal to 0, and for the low frequencies tangent in Xe will be equal to uh, infinity, and Xc divided by R, Xc over R. this angle x over r will be equal to infinity, and tangent inverse infinity equal to 90 degree. And for the critical frequency fc the theta is equal to 45 degree. So a low pass, for the high pass, the low frequencies, the theta is equal to 90 degree, and for the higher frequencies theta is equal to 0. Okay, this is the summary of the previous results of high pass filter. Okay, so the RL circuit similarly also acts as the high pass filter, but we will get the output from the L. Okay, so again this will be your homework. You have to do the same calculation of that, and the same, you have to draw the same sketch for this RL circuit of high pass filter as we have done in RC circuit. Okay. Okay, the band pass filter, as the name revealed. So how the circuit diagram will look like? It will actually we have to cascade the high pass filter and the low pass filter like this. So the high pass filter will be placed first and the low pass will be placed second. So it means the input side will be the high pass filter and the output side will be the low pass filter. So the output will be uh, okay. So this portion is the, you know, output from the capacitor. It means this is the high pass filter, and the output from the resistor is the low pass filter portion. Okay, and we are cascading, means in series with these two. Okay, so we will get, so how we will get uh, the band pass filter by cascading these two filter. Actually what will happen, uh, the low the frequencies will try to pass through these. So the low frequencies will be blocked by this high pass filter. It will only allow the high frequencies. Okay, now uh, what it will do, it will block it will block the high frequencies and allow only a range of frequency. uh, Considering this case, actually the low frequencies will be blocked. This will be blocked, and it will pass all of these frequencies. Okay, now when these frequencies will trying to pass to this low pass filter, so what actually happen, it will block this portion, this high frequency portion, and allow only this portion. So this was the case by the this high pass filter, and this is the result of this low pass filter. So combining these two results we will get this band pass filter. Okay, this is the fc of high pass filter, and this is the fc of low pass filter. So uh, it means this actually the initial range of the band pass filter, and this fc of low pass filter is actually the final range of the band pass filter. Okay, so we will discuss the band stop and the numerical of these filters in the next class. So that is all for the moment. Thank you.